Yeah, hello everyone. Good evening. Welcome you all to the Week 3 live interactive session. In Week 3, the video content majorly covered what is known as process and the various system calls that are used to create or manage the processes. Okay, so we will take a look at it. Okay. So just last once, please confirm if I'm audible, then we'll get started.
Yes, ma'am, audible.
Yeah, thanks. Yeah, so what is a process? The definition of a process. So normal definition is a program. A process is nothing but a program in execution, right? So in the I think earlier class we have seen right a simple hello world program, and we have also seen like when we are while putting in a while loop, we have seen like when we are executing that program we can see that a process is created and we could see the process ID also. Correct. So when we a simple hello world program like no, this doesn't work in C. It's like assume it's Python kind of. This, then, okay, now when we compile this, how do we compile this? This will be CC followed by file name dot C, right? Then we will get what is known as a dot out as the output. Now when we execute this dot slash a dot out, a process will be created and this process will execute this instruction and then it will print hello world on the screen. Correct? So this is how normally when we run the Python programs or Java programs or all those things, this is how we execute, right? So we write the program, we compile it, and then we execute. So when we execute the program, process gets created, and then that process will take care of performing whatever operation we have written in the program. Correct? So when we say a process contains like some uh, what to say. There are certain components in a process. We can say a process comprises of code, data. It will have stack. It will have heap. Then operating system does a lot of account keeping state in the operating OS, and also it will also have the kernel stack. Okay, so how the operating, sorry, the process memory map or address map looks is like this will be the virtual address map. How it will look like is, this is where the stack will be. Stack grows downwards and heap grows upwards. Then we will have the data, then the instructions for the text. So this is how the memory layout, virtual memory layout of the process will be. Okay, process address space. So we have already seen this virtual address and physical address, right? So every process that we create in the system will have a virtual address map for it. Okay, and all of this will start with 0, and the address will be always from 0 to max size. So here all the instructions, the program instructions that we have written, which is compiled, all that will be present here. Data will comprise of all the global variables. Heap will contain the dynamically allocated memory, and stack will contain all the from this particular program, the function calls and all those will be present in the stack. Okay. So this is how the, on a simple manner, this is how the virtual address map of a process will look like. So if in the operating system, if we have, and additionally, each process will have a page table also. So if in the memory we have process 1 and process 2, so process 1 will have its virtual address map and page table. It will have its page table. P1 will have its page table. P2 will have its address map. P2 will have its page table. Same way, how many ever processes we have, all of them will have a virtual address map and will also have a corresponding page table in the kernel. Okay, and all of these virtual address, all of them vary from 0 to max size. 0 to max size. 0 to max size. And all of them now we know we have only a single RAM, right? And this RAM, all these the frames or the pages from all these processors will be mapped onto the available physical frames on the RAM. So via the page table, these processors will access the physical RAM. Okay, it will not be a direct access, but via the page table. All the frames, the page table will contain. Okay, this is 1, 2, and here we have 0, 1, 2, 3, 4, 5, 6, and 1 is kept in probably 2, and 2 is kept in 5. Okay, so like this, the mapping will be there for each of these processes. Okay, so now the processes will have this, and from here the mapping will come to the physical memory. Processes will have, and from here this will come. Okay. So that's how the memory is allocated and the processes gets executed. So the major advantage of this virtual address map is that since we are having this from 0, one can take this frames and put it anywhere in the physical memory. So we call this feature as it becomes highly relocatable. Okay. Then additionally, these virtual address map, each process will have a kernel data also. So the one that we saw just now was only for the process. Additionally, there is this kernel data also available in the virtual address space. In the virtual address space, this each process will have this is the user process data and also the kernel data will be present. For each process, this will be available. But in the physical RAM, this kernel data is always placed at the bottom, and there will be only one copy of this. All the other process P1, P2, P3, Pn, all of them will access this same. P1 will access the same, P2 will be also accessing the same, P3 will, and P4, all of them will be accessing the same. So there won't be multiple copy, but in the virtual address space, for every process we will have a copy, whereas in the in physical memory, a single, it is only available, it's not replicated. Okay. And always the kernel program, the data, text, all that is always kept at the bottom, which starts from 0. This is done so that the mapping from kernel, the physical address to virtual address can be easily done by adding and subtracting the max size. Okay. So basically, we can tell that the process stack, each process will have as we saw, we will have the kernel part and the users part. Additionally, inside the kernel, we have the kernel stack, and here we have the user stack. Okay, so a process, there will be, each process will have two stack. One is the user space stack, and the other is the kernel space stack. Okay. Then, so this is about how the layout and all. So in the kernel, each process is identified using something called as a process control block. Each process and this process control block, actually it is a big structure which contains various fields. So in x86 it is struct proc, whereas in Unix it is different. But what they hold will be the same. So there is something called there is a size field, then there is a pointer to the uh, page table, there is a pointer to the kernel stack, then there is something called process state, then PID, and there are many such, then the name, there are many such fields in the process control block. Okay, so as we see, this is the size of the process memory, this is the pointer to the page table, kernel pointer to the kernel stack, the state of the process. We will see that what is a state of a process, then the number of open files, then there is, this is the executable name, and what is the present. A lot of details are kept in the process control block. Okay, so now the first thing that we can see in the process control block is the what is known as PID. Let's see PID first. PID is nothing but process identifier. So if you have a Linux machine or a Ubuntu or Linux based machine, we can go to the terminal and check ps minus ax, and you can see the list of all processes running, and all the process will have something called as a PID, which will be there on the leftmost part. So this is an identifier which uniquely identify the process in the operating system. Okay, so typically this is incrementally assigned by the operating system. So that is process ID. Then the process state. So basically, processes have majorly four states. One is new, ready, block, and running. In x-physics, the terminology is slightly different. This is called embryo. This is called runnable. This is called sleeping. And the other is running. Okay, so when we first create a process, the process will get into the new state. Okay, then from the new state, it goes to what is known as a ready state. Okay, and from the ready state, it goes to running state. And then if it completes, it exits. Sometimes from the running state, it goes to the block state. Like for example, when we are doing a like input output operation. For example, we have a C program. Okay, and we want to add two numbers A comma B. Okay, so first what will, if we want to add two numbers, we will tell enter the numbers. We want to take it from the user. What are the number that we want to add? Then we use a scanf A comma B. Correct. So then some, let this be printf summas percentage d comma. So okay, so if we run such a program, what happens is first on the screen, enter the number will come. After that, the scanf is the function that waits for input from the user. Okay, so until the user gives like A as some 10 and B as 15 using the keyboard, the program will be waiting there for the input from the user. So during this time, from the running state, the program normally goes to the blocked state because currently we are waiting for a input from the user, right? So from the running state, the process will go to block state. Now, once the user gives the input and press the enter, the program will be again go back to ready state, and from the ready state, it will go to the running state. So this new is when the process first gets created. Okay, this is when it is created. Now, after the process is created, some initialization has to happen. The PCB has to be filled by the kernel. Certain those things has to happen. Once all that initialization, allocations, everything is done, the process goes to the ready state. And from the ready state, it starts running as and when the CPU is scheduled, as and when the process gets scheduled, or as and when the process gets a CPU, it will be running. Okay, now run from the running state, it will come to block state if the process is waiting for some IO or some operations. Then from the block state, again it can go to ready state and then run. So these are the and also we can also go to, from running, it can also go to ready. That is when I will explain that the concept of CPU scheduling. So normally during the scheduling, each process will be given the CPU for a fixed time quota. So once that time is done, the process will be moved out and another process will be scheduled. So that is when the process will move from running to ready state. Okay. So these are the state of the, so this process state. Hello?
Excuse me, ma'am.
Yeah.
Ma'am, I want to know in the C program, the scanf line, the ampersand sign will also appear with the variables A and B.
Yeah, it will be there. I just missed it. I mean, I'm just writing down, no, ampersand will be there. Yeah,
Okay, ma'am.
syntax. It's a syntax error. I just missed it. Okay. Mm, yeah. Okay.
Yes, ma'am.
All right. So this is about process state. So now let's see how the process moves from ready to running. I told you there is something called the process must get the CPU. So we call operating system uh, takes care of a sure. That's fine. Yeah, CPU schedule, we call it CPU scheduling. That is the processor. There are multiple processors. Let's think the ready. This is as a ready queue, wherein we have P1, P2, P3, P4, P5. Okay, and these are all these processes are in the ready state, waiting for to execute. So, when the operating system does the scheduling, it will first give the CPU to P1. Then, after that, it will give to P2. Then, it will give to P3. So, when it gives to P1 will execute for some T time. Then, P1 will go back to ready state. Okay, P1 will execute for T amount of time. Then P2 will be given the CPU. So P1 after T, P1 will go to ready state. Okay, P2 will become running. Now after P2 is done, P2 will now go back to ready state. And P3 will become running. Then P4. Then P5. After one round is done, if P1 still needs the resources, P1 is still in the ready queue, again P1 will be given the CPU, P2. So this goes on. So there are certain scheduling algorithms based on which the CPU will be given to the processes. Some of the simplest one is first in, first out scheduling algorithm. So we have this ready queue wherein P1 came first, P2 came second, P3 came third, P4 and P5. So the order in which they came into the ready queue, in the same order, the CPU will be given to these processes. Okay, that is the first in, first out. Scheduler. Another one is shortest job first scheduler. That is, it will see the it will see how much time each of these process takes to execute, and then it will give the CPU to the process that requires smallest amount of time. So based on the time each process takes, an order will be created, and in the increasing order, the processor will be given to the processes. Another most common one is the round robin scheduler. Round robin scheduler is what I have just told. So each process will be given a quantum of time for execution. Okay. So first, then in the FIFO order, in a round robin fashion, the processes, the CPU will be given to each of the process. So first P1 will be given, then P2, then P3, P4, P5. Then again, this will come back here. Again, then P1, P2, P3, P4, P5. and this will continue until all the processes gets executed. Now, after this two with the two time quanta, if P1 completes its execution, then P1 will move out of the ready queue. P1 will go to the exit. P1 will exit the queue. Then after P5, P1 is not there means P2, P3, P4, P5. Again, this will continue. So this is an example of a round robin scheduling. So the CPU scheduler is another functionality of operating system. So the scheduler will trigger to run whenever the timer expire. No, it will move this process out to the ready queue and bring another process to the running state. So from the ready queue, when this timer, this time quanta is there, no, so there will be a timer, and whenever the timer expires, whatever is currently running, it will be moved to the ready state, and then the second person in the queue will be brought into the running state. So this is how the CPU scheduler works. So it will pick the another process from the ready queue, and then additionally, when I'm saying like P1 will go to ready and P2 will come to running, like there are some other additional operations that needs to be done, because we have to save this process, and then next time when the time quota comes, P1 needs to start executing where it stopped, right? So these information needs to be saved. So when P1 is moved from running to ready, we call this a context switch, and a lot of information about P1 needs to be saved. We call the context of P1 need to be saved, so that next time when P1 gets the CPU, it will start execution from where it stopped. From where it stopped. So that will this operating system takes care of doing this context switching. So P1, a lot of P1's information will be saved in the PCB, and everything will be saved, and then like the register values, a lot of content in lot of these registers and other places needs to be saved, and then the next process will be brought in and start executing. Okay, so with the CPU scheduling, what is known as a context switch also happens, and operating system takes care of doing this. So that's about the process states. The next one is there is also something called as page directory pointer. So page directory pointer is nothing but the in the PCB there is something called page directory pointer. This will point to the page table. And there is another thing called trap frame. So this also contains all the register, the stack pointer, instruction pointer, all those details. Okay. So this will be in the kernel stack actually. Trap frame will be in the kernel stack, and when context switch happens, actually the trap frame, the details, because the current where the currently where the instruction pointer is pointing to, that needs to be saved, so that when the process comes back to the running state, it can get started from the same place. So the trap frame, the register information indices, pointers in this trap frame also will be saved. So that is another entry in the PCB. Then, yeah, the context pointer. Okay. So then so we have seen a couple of information in the PCB, of which the major thing is process ID, this process state. Then now let's see how we create a process, how the processes are created. So we can create the process by cloning. So one system call that is used to create the process is fork. Okay. So fork is the system call that is used to create the process. So what happens is we will have one process which we call as the parent process. Okay. We will have a main. We will have some X, Y, Z, some instructions here. Okay, so this process is already done. Then here we do the fork system call. So when we invoke the fork system call, a new process, a new process which is an exact replica of the parent, new replica gets created. Okay, so I'm not writing, just an example. So we will have after the fork, we will have a parent process P and a child process C. Okay. So this system call will get executed in the kernel, and then the kernel will take care of creating a new process, that is the child process. So during this execution, once the control reaches here, this is a system call. This call goes to the kernel, and the operating system will then, since it's a fork call, operating system will take care of creating a new process. Since the process is created from another process, so that becomes the child process. So this main process, this main process becomes the parent, and the newly created process becomes the child. Any doubts?
No, ma'am.
Okay. So let's see the same example. Let's get these PIDs and all. PID and so fork system call will return the process ID of the child. Okay. So this is the main process, parent process. So from the parent, so this is the instruction in the parent program, parent program. Now if PID is greater than 0, printf parent. Else if PID equal to 0, please don't bother about the syntax. And else it is an error. Okay. So what does this mean? This means that when a parent is executing, okay, the parent P1 is executing. So in between it makes a fork. So what happens is a new process starts executing here. A new process gets created, which is the child. And what this fork will return us, every process will have a process ID. Okay. So this fork will return the PID of C. Child's PID will be returned to the parent. PID of C will be returned to the parent. Whereas in the child, it will be 0 only. So how it works is, so when what happens when a fork system call executes is at this point, the child also will start executing at this point. Immediately after the fork, whatever is the instruction, from that instruction, the child will also start executing. So the parent will continue this set of instruction. The child also will be executing the same set of instruction. Okay. So this assignment, in this assignment, what happens is in the child process, the PID gets assigned as 0. Whereas for the parent process, the PID of the child will be assigned. So now when we do this PID greater than 0, so you have to imagine, okay, two processes are there which are executing the same code. Okay, and for one PID is 0 and for the other PID is some non-zero value greater than 0 value. So for the parent, the PID, fork will return the PID of the child, which will be greater than 0. So this check will be correct for the parent process and print parent will be printed. Whereas for the child, this will fail because what it gets is 0. So this check will succeed for the child and print child will be printed on the screen for the child process. Okay, is this is clear? So this has to be clear. So when we create a new process using fork, the entire both of them will have the same set of instructions. Okay, so whatever after fork, whatever instructions we have, this will be the same. So we told, right, this is creating a process by cloning. So it's the literal replica of the parent will be created, but it will be a different process. Okay, that process will have different process ID also. Okay, so when the fork is executed, so a new process gets created, and to the parent, the OS will return the child's process ID. To the child, it will be 0 only. Okay. So this is how the fork system call works. So as I said, there is it is the replica of the parent. Initially, the page table, the memory, everything will be the same. Okay. So when we do a fork, there is a copy of the whole. This is done. Page table, the memory layout, everything will be initially shared. Okay, so how it will be? So initially, if this was the parent page table, and okay, this is in the RAM. If these were the places, like for example, this frame, and this and this. So if these were the parent process page table, the same replica will be created for the child also, and child will also have mapping to the same set of places. Okay. Initially, this is how it will be. So both of them will have the both of them will be referring to the same RAM. Now, what happens is now if we make some changes in the child's program code, like if we, for example, if we want to, if PID is greater than 0, and we are just printing some I equal to 0, printf parent and percentage d I. Now, if PID equal to 0, what we are doing is I equal to I plus 1, print child. Okay. Now, what will the value of I be printed for parent and child?
Ma'am, for the child, it will be 1.
Okay. For the child, for parent, it will be 0, and for child, it will be 1. But we just told, right? Both of them point to the same place. Then how is it done?
Ma'am, a new block will be created in the memory for the child process to store the value.
Correct. So whenever there is any changes made, whenever there is any change made to any of the data, then a new allocation will be done. This is for the child. This new allocation will be done, and then this will be removed, and this will be added. And then the page table will be updated. So initially, when starting off, both of them will have the same page table and the mapping. But as the process execute on a demand basis, the page table and the memory mapping gets updated. If both of them have a different set of code being executed, then accordingly the memory will also get updated and the page table also will get updated. Chart. Okay. So this is one example. Another example, another way of fork is like in this we have seen that we are just having some if check simple same code we are executing. Now, what if I want to execute a completely different program in the child thread? So we use the system called as exec. Okay, so using this exec system call, what we can do is we can compile a different program, and then using the exec system call, we can make the child process execute that particular program. For example, we have a fork, and we can mention that if PID greater than 0, do some XYZ things. Else, when PID equal to 0, we can do this exec, and we can tell, like for example, I have compiled some hello world and I have created an a.out. Okay, as the object file, I can tell that a.out and then some parameters. Then once this execution is done, we can exit from the. So with exit, it's another system call which means that the child process completes execution. So the process will exit. It will be like it's done, it's dead kind of. The execution is completed. So this is another way of executing a different set of code for in the child process. In this scenario, again, when in the child process, a new different code is being executed, right? So all this the a.out which is there in the disk, it will be copied from there, and then on the and then it will be updated in the RAM. Okay, so P1 parent will have a page table, child will have a page table. Child page table will now have a different set of mapping. Initially, it would after the fork, it will be the same. But once it comes here, XCLP, when we tell that okay, this is the object code that we want to execute from the child process, that code will be retrieved from the disk, and then mapping will be done, and then accordingly the page table and all will be updated, and the execution will go ahead. Okay, so that is about exec and fork. Then we have seen that yeah, so that is and there is this concept of uh, process tree. So initially when the system boots up, which is the first process that gets created? So we have init. So this is the first process that gets
Init
created, and then init will call multiple processes like this. Okay. So the every like what do you call in Linux and all, normally when the system boots up, first init process is created during the boot process, and then after that, lot of other processes and daemons are created, which keeps running in the background. In an infinite manner. And those takes care of a lot of aspects of the OS and kernel functionalities. Okay. So if we using fork, if you want to see an example, like we have a fork, like let's see this parent-child relationship. Okay. Now, if I have a program where I am executing fork like this, how many children will be totally? How many children will be created?
2n minus 1.
2n minus 1. So let's see how it is done. So first we have P1. So the first call, what will happen after the first fork? How many process we will have?
2 processes.
So we will have P1 and C1, right? Now,
Yes, ma'am.
P1 and C1 will be here. So from P1 again a fork is called. From C1 a fork is called. That is this guy. This fork is called. So what will happen? So initially we had P1. We created P1 and C1. Now from P1 again a fork is called. So what will happen? P1 and then again from C1 fork is called. So C1 and C2. So now how many process we have? 1, 2, 3, 4. Correct? Don't count this P1, P1, C1. Okay, no. No, you're not getting it?
Ma'am, is both the C2s are same?
No, 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 sorry. This is C3.
Thank you.
Yeah. Yeah, now what happens? Now we have, so now all the four of them are here. After this fork, all the four of them will execute this fork. So it's equivalent of calling a fork from P1, fork from C2, fork from C1, and fork from C3. So now how many processes will be there? So from P1 again a fork is called. So we will have P1 followed by C4. From C2 again a fork is called. So C2 will be the parent and one child C5 will be created. Now from C1 there is a fork. So C1 will be the parent and child will be created. Again from C3 when we have a fork, C3 will be the parent and 7 will be created. So totally how many processes we have after that execution? After executing fork 3 times, how many processes do we have total?
Power n minus 1.
1, 2, 3, 4, 5, 6, 7,
8.
8. So 2 power
Power 3
total
n.
number of processes 2 power n, where n is the number of times we invoke fork. So if we invoke it once, we will have 2 processes. So you're getting this idea, like what happens is, as we know that the entire instruction, everything is replicated, right? So at this point, the parent and the child will be created, and then they go to this next instruction. Both the parent and the child will execute this. So this is the initial fork, parent and child. Both of them will execute this second fork. So here it's equivalent of a fork here and a fork here. Correct?
Yes, ma'am.
Okay. It's 2 power n, okay, not 2 power n minus 1. So when if you get this kind of question sometimes comes in gate. So if you get have this, you can draw this free and it will be easy to figure out. Okay, now we have seen fork, which is process creation. Now process termination. So what is the system call used for process termination?
Exit.
Yeah, so exit is the system call used for process termination. So this will be when it is voluntary, like the process calls exit, so it's voluntarily exiting. Sometimes we kill the processes, right, using control C, control Z, and all that. So using that is another way of process termination, and that is involuntary. So when we do a control C, right? So we give a signal to the kernel that I want to stop this execution. So then the operating system takes care of killing the process. Okay, that is involuntary termination. Okay, now when this processes gets terminated, what happens is all the we know when a process is created, the PCB is created and there are a lot of entries are updated in the PCB and all. Okay, now when a process is terminated, it doesn't happen that the PCB is cleared, the page table is cleared, everything is cleared, all the memory allocations, everything is cleared. Instead, these all of them are retained, and the process will go to what is become what is known as a zombie. Okay, when a process terminates, it normally becomes what is known as a zombie, which means that there is no execution happening, but the PCB in the operating system will still exist. So yeah, so PCB still exists, but program is not running. That is okay. Why we don't do this is because sometimes there are certain the parent processes would be reading the status of child process. So when we exit the child process, and if we clear the PCBs, then the parent will not be able to read the status, like how did it execute, how did it execute and exit, is the exit properly, or was there any error code when the child exit. All this information, the parent process will not happen. Sometimes the parent will also be waiting for the child to exit. So if we so due in the wait, the parent will be actually looking at the status of the child process. So to let the parent know that okay, the child have exited, and this is the error code, or this is the exit status information, we retain the PCB in the operating system. Okay, until the parent reads the status. Okay, so it will be in zombie until parent read the status. Once the parent read the status, this will be the process will be read. Once parent reads, process will be reaped, which means all the allocations, everything will be cleared. But if the process doesn't read, this will continue to be in the zombie state. If parent doesn't read, process will remain in zombie state. So this is the problem with this is that there are a lot of memory allocations and all retained, even though the program is not executing. So unnecessarily the resources are blocked. So which is like a resource leakage. So there is a mechanism which the operating system takes care of doing. So there is a reaper process which will check periodically all the zombie processes, and then takes care of clearing it up. Okay. So this is the zombie state. So when the process exit, just keep in mind that it goes to the zombie state until the parent reads the state. Okay. Another thing is orphan processes. So this happens when the parent exit before the child. That is, if we have like this, and if this parent process exits, then this child will be like an orphan. So what happens is all such orphan processes are made as children of init process. Okay, so they normally it happens when the parent crashes. Sometimes when we want the child to be in a detached, like a background process. When we want the child process to run like a daemon in the background, then normally this is a intentionally we make the child process orphan. But if the parent crashes due to some issue or bug, then it is like unintentionally the process becomes an orphan. Okay, so that was about like yeah, so we pretty much talked about all the like fork, exit, wait, then zombie, and okay, so all of these are done. Okay, so now we will look into the previous year's questions. Okay. Right. So that I'll do copy paste in the chat. Yeah. Okay. Match the following. So A is I node, B is new state,
Ma'am, the answer will be A3, B1, C4, D2.
okay. Yeah. So what is the answer?
A3, B1, C4, D2.
Any other answer? Okay, so what is I node?
Which stores the metadata.
Okay. Yeah. So yes, I node stores the metadata. New state.
PID is assigned to a process.
Okay. Wrap frame.
Never exist.
Wrap frame. Trap frame is used
For
for
restarting process.
restarting process after context switch, and init process will never exit. Okay, so A3, B, B1, C4 and D10. Okay, the next question. I think this we should be able to settle. We have N for system calls. That is the total number of processes created. So if we have N for system calls, what is the total number of processes created?
To the power n.
Sorry?
2 power n.
Okay. 2 power n, yeah, we will have 2 power n processes created. So the next one is a true or false statement. State if it is true or false. So process whose parent
Ma'am, false.
Okay. So process whose parent exited before the child is an orphan process. Is that true?
Yes, ma'am.
And a process can be zombie and orphan at the same time.
No, ma'am.
Right. If it is an orphan, then it cannot be a zombie. Correct. So the statement is false. Okay, so this is a code snippet. So these are previous year's questions, okay, assignment questions. What is the output of the following? I will write the options here. Yeah, so what is the correct answer? Try this out.
I think option number 1.
Okay. Any other answers? Any other answers? Any other answers? Okay, so you are saying u equal to x plus 5 is the answer.
Yes, ma'am.
So shall we take an example and see?
Yes,
Maybe
ma'am.
a equal to 1. If we take a equal to 1. Okay. So for the child, that is when the PID is equal to 0. So a is equal to a plus 5, which is 1 plus 5, a equal to 6, correct? So the value of u is 6. And what will be the value of x for the parent? A equal to A minus 5. A equal to 1 minus 5, which is minus 4. Now, if we take, you're saying u equal to x plus 5. What is the value of x? X is minus 4, right? So, minus 4 plus 5 is 1. But u is 6, right? Yes or no?
4, ma'am.
Yes,
U is equal to x plus 10.
So, is that correct then? Shall we try option 2? Again, let's take a equal to 1. So, u is 6 and x is minus 4. Option x is equal to u 6 plus 5, which is 11. So, this is also not correct. Now, let's take option 3. X equal to u plus 10. So we have for a equal to 1, now a equal to 6 and x equal to minus 4. This value that we have arrived is correct, right? No doubts on it, no? X and u. Okay. So x equal to u plus 10. 6 plus 10 is 16, which is again wrong. Now let's see the other option, which is u equal to x plus 10. So minus u equal to x plus 10. X is minus 4 plus 10, which is 6. What is the value of u we have? It is 6. So this should be the right answer, right? Okay, think on it. Okay. Let's go to the next question. Okay. This is again true. Which of the statement is false? Init is the first process created using booting. Init is daemon process. Init process have process ID 1, none of this. So, which of these following statements are false? So,
Ma'am, option
init is
number
the
D.
first. Sorry.
Option number D.
So this is correct, right? Init is the first process created using booting. So this is correct. It's a daemon process, correct? It has process ID 1. So all of them are true. So none of them is false, okay? None of this is the answer. So now the next question. Program. So student wrote a program and used PID equal to fork function call. PID returned is 5119. Now, which of the following is a which of the following is true about process invoking fork? Process is a parent process. With PID 5119, B process is a child. Its parents PID is 5119. C process is parent. Is a parent. Its child PID is 119. D process is a child process. Yeah, so a student wrote a program and used PID equal to fork function call. And this call have returned the PID as 5119. So now which of the following is true about the process that is invoking the fork? So the process that have invoked the fork is the parent process, right? So process is a child process is wrong. This is also wrong. Now these are the two options available. So in the the PID returned is 5119, which means that the PID of the child process is 5119. So process is a option A says process is a parent process with PID 5119. That is wrong. Parent process ID is not 5119. C says process is a parent process and its child PID is 5. So this is the right answer. Correct. So from a process, So it is equivalent of the statement main. Okay, and the PID returned is 5119. So this 5119 will be the PID of the child process, and this the main function that invoked this fork is the parent process. So option C is the correct answer here. In any doubts, confusion? Next is which of the following is false? Okay. Okay, these are now like I'll copy paste in the chat. So the question is which of the following is false? Okay. So the first statement is process contains code plus data plus heap plus stack plus process state. Second is one program can be, I have typed it in the chat, you can check the chat. Second is one program can be used to create many processes. Third option is process is not a unique isolated entity. And third is code plus static program contains code plus static and global data. So which of the
Ma'am, option number C. Process is not a unique isolated identity.
yeah, so that is false here. So process is actually a unique isolated entity. So that is the correct answer. So the next one, okay, I will write here. Okay. Yeah, so the state transition that occur due to scanf system call. So there is this ink, I think we discussed during the class. A scanf percentage D slash n ampersand A exit 0. So what is the state transition? That occur due to scanf system call. New to ready to running. Running the block and block to ready. So what is the state
Ma'am, option
transition
number
that
C,
will
running to plot. Ma'am, option number 3.
okay running to blocked? Any other answers? Yeah, so running to block. So scanf will wait for the input. So that time the process will move from running state to blocked state. Okay, so this is the answer. The next question is, can we say we'll copy paste. State true or false. I'll paste it in the chat, okay? Okay. So, yeah, if the parent and the child process share the same page table, does this mean they share the same page frames in the RAM?
Ma'am, option number D, both statements are true.
COW is copy on write, creates a copy of the shared pages if it is changed. All further changes are made in this new page. So this is true, right? Copy on write. Copy on write is nothing but if in the child process we make any changes to any of the variable or anything, when the write happens, operating system gets the signal and it will create a new frame for this for the child process. So the statement is true, and further on, all the changes are made to the new page. And initially, if the parent and the child process share the same page table, does this mean they share the same page frames in the RAM? This is also true. So the answer here is both the statements are true. So next is match the following. So A init dot D created when system right. So options are A1.
And the answer will be A3, B4, C2, D1.
Okay, I'm not. Okay, let's discuss the answer. So init.d, it is the first process created by the kernel while booting. So, oops. So A to 3. Now B zombie. Zombie created when system call occur. Yeah, allows a parent process to read the status of child. So zombie is 4. So B to 4. Child process is created when system call occurs. So C to 1. And tab frame, the EAX register is cleared when this is created. So this is in the trap frame. So D, so this is the option. Okay. So state true or false. I will copy and paste it in the chat. Yeah. In memory mapping, the entire kernel is mapped into process address space, which helps the user's process to easily access the kernel data. True or false? In memory mapping, the entire kernel is mapped into process address space, which helps the user process to easily access the kernel data. Is it true or false? Does user process access kernel data? User processes cannot access kernel data. Kernel can access user data. So the statement is false. Okay. So the next one is arrange in order. So these are the various things that happen during a process creation. So now arrange them in the order. The options are A, C, B, D, E, D, A, B, D, B, C, A, C, B, and D. So, what happens at first in the order? Like, so first is change state to runnable. This should be the last one. Copy page directory content from parent to child. Copy trap frame from the parent process. Change state to embryo. So first thing that happens is change the state to embryo or new. After that, the page directory contents from the parent is copied to the child. Then the trap frame from the parent process is copied. And at last, we make it, once all these are done, we make the process state to runnable. Okay. So option is DBCA, which is DBCA is D. Now, next one. Wait system call inside parent process. So what is the answer? Wait. So the question is wait system call inside the parent process returns the status of the child. Wait system call inside the parent process returns the status of the child. Okay. What does it return when it is called inside the child? So if a child process calls a wait, what does it return? So how wait system call works is if this particular process which is calling this wait system call is not a parent, then actually it will return -1. So option A is true. Returns -1 when it is not parent of any other process. Okay, so that is the correct option here. See, the next one is state true or false. This is the last question. True or false? It's equal to system call replaces child process with a new program file W. This is true or false? XCLP system call replaces the child process with a new program file, but the process ID of the child process will not change. True or false? So the statement is true. Okay. So what happens is the child process will be created and then it will go get the program file and update it in the new page frames will be allocated and that will be updated. But the child process will be the same. Process ID will not change. So this is true. So yeah, with this like pretty much done for the day. If you have any doubts, we can discuss. I mean, if I know, I can help. So if there are no more doubts, then we can close the session. Thank you all.
Thank you.
Thank you. Okay. Thank you all. I'll close the session.